I'm going to try and explain, as best I can, where the four forces of nature come from. I've always hoped that one of the TV physicists like Brian Cox or Jim Al-Khalili would do something like this on the BBC. They'd do it far better than me, the presentation would be a lot slicker, and they're real physicists, they'd know what they're talking about. I'm just an amateur student who reads books on this stuff. But as far as I know, no one has really done this stuff at a level that non-mathematicians can appreciate. So I'm going to do my best to convey what I've picked up from various quantum field theory and particle physics texts. There are four fundamental forces in nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. At first glance, they all seem very different from each other. Gravity is the force that holds me onto my chair, that holds the Earth in orbit around the Sun, that holds the Sun in orbit within the galaxy, that holds galaxies together in clusters and superclusters. And except at the very largest of scales, it's gravity that dominates the universe. The electromagnetic force holds atoms together. It creates molecules and so is responsible for chemistry and biology. Almost everything we experience in everyday life that isn't gravity is electromagnetism. Although electric and magnetic fields know no bounds in terms of their reach, most everyday objects are electrically neutral because positive and negative charges balance each other out. The strong force binds quarks inside neutrons and protons. It holds protons and neutrons together inside the nucleus. It's so short range that we aren't even aware of its existence outside of the nucleus. Then there's the weak force, the strangest of the four forces. Rather than binding things together, it causes them to change from one type to another. It scarcely seems like a force at all. We can compare the relative strength of the forces as follows. If we take electromagnetism to have strength 1, then the strong nuclear force is around 100 times stronger. You can see this fairly easily from the size of a nucleus. The largest nucleus is roughly about 100 protons, and at that point the strong nuclear force can no longer overcome the electromagnetic repulsion between protons. The weak nuclear force, compared to electromagnetism, is about, now let me just get this right, 0.00000000001. So that's about 10 to the minus 13 times the strength of electromagnetism. Now that seemed like a huge, or rather a tiny number compared to electromagnetism, but we'll see why it is that the weak nuclear force is so weak when we come to discuss that in a bit more detail. Gravity is very much weaker than electromagnetism. Now, to give you an idea just how weak gravity is, just look at the fact that I can pick up this pen. The only thing that's holding that pen up is effectively electromagnetic forces being expressed through chemical reactions in my not very muscular muscles. But there's an entire planet trying to pull down on that pen right now. Every single atom on planet Earth is pulling down on that pen, and yet I can just pick it up really quite easily. And if you want to compare gravity to electromagnetism in terms of the strength of the two forces, well, you might think maybe it's 100th or 1,000th or 10,000th, but you actually have to go quite a bit further than that to get the strength of gravity compared to electromagnetism. It's actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 26, 27, 28, 29, 30, 32, 33, 34, 35, 36, 37, 38, 39, 40. It's about 10 to the minus 40 times the strength of electromagnetism. Now, this number is currently unexplained. Despite the weakness of gravity, gravity always wins in the end. The other forces have multiple charges or short distance scales. Everything feels gravity. The more stuff you add, the bigger the gravitational force becomes, until eventually it acts over the entire universe. We can classify particles of matter according to which forces they feel. All matter particles have spin-half angular momentum, but they vary in the forces that they feel. Up and down quarks feel the strong, the electromagnetic, the weak, and the gravitational force. Electrons feel the electric force, the weak force, and gravity. Neutrinos feel the weak force and gravity. Now, neutrinos, which feel the weak force, are hardly detectable. Millions pass through us every second. In fact, they pass right through the Earth, even right through the Sun, and they scarcely even notice that they're there. You need massive detectors and need to wait a very long time before you detect a single neutrino. If there are particles out there that only feel gravity, well, no one really knows how they're going to find any particles like that. We have enough difficulty just finding neutrinos. Never mind finding particles that only feel gravity. And as the number of forces felt by a particle increases, so does their mass. So electrons are heavier than neutrinos, up and down quarks are heavier than electrons. The reason why particles have the masses they do is not understood. In fact, it's worse than it appears in this table. Each of the particles appear in 3 generations that differ only in their mass. For example, the electron has a heavy partner called the muon. And the mass of the muon is about 200 times the mass of the electron. And it has an even heavier particle again called the tau, which is about 3,600 times the mass of the electron. Why these heavy versions of the electron and the other particles exist, and why they have such dramatically different masses, is currently a complete mystery. Despite these unknowns, and despite these apparent differences between the 4 forces, there's a very beautiful explanation for how they all arise. And they all arise in a very similar way. And this isn't just a hand-wavy explanation either. It's at the core of the standard model of particle physics, the most successful and accurate theory of physics ever constructed. So in the next video, I'm going to start to explore this idea about where the forces come from.